No, that doesn't work.
All right, so last example from the optimization set. So we want to find the area of the largest rectangle possible that can be inscribed in a semicircle, radius r. Okay? I want to find the largest area possible of a rectangle that can be inscribed in a semicircle of radius r. Okay, so it's always a good idea to think about, what am I trying to maximize or minimize? What am I trying to maximize or minimize?
So you're maximizing the area?
Area of what?
Rectangle.
Area of rectangle, right? So that's that's the end result goal. Maximize area of rectangle. Okay. Plug in. I'm going to maximize the area of my rectangle. So I know that the area of a rectangle is just like x times y, right? Or just length times width. I shouldn't say x times y because I haven't made any variables yet. Now, here's the technique that I'm going to use out of this, okay? Because I want to create this on a coordinate plane so that I can make things a little bit more manageable for myself. I'm actually going to use for my axes here. Okay. So here's my semicircle of radius r. Oh, that's pretty good. A little bit to the right. That's okay. Semicircle of radius r. Okay. And I want to put a rectangle in there. That has the biggest area. Right? The reason why I am putting this on a coordinate plane is because maybe I can create another equation out of this. Maybe I can create an equation because I'm going to need two, right? I know what I'm going to do for my area. Area is just length times width. But obviously, I'm going to need to use another equation so that I can plug that into that area formula because I can't have two different variables when I go to differentiate. Okay, so here's what I'm going to do. I'm going to treat this this here as the x value because, like, look here. Isn't this just x times y? Right? Some coordinate x times y, some point out there, x times y. And I know that coordinate, since it's got to be inscribed within that circle, that coordinate has to lie on that semicircle. It has to lie on the equation of that semicircle, which we'll use here in a second. So if this is x and this is y, what are the dimensions of my rectangle? What is the true area of this rectangle? 2x times y. 2x times y. Okay, just because the length of this thing is now, if I've got x on one side, that means I've got x on the other side because, I've just basically said that I've set it up so that this is through the center line here. X on one side, x on the other side. We'll just treat this as like negative x comma y, right? So it's two x's and then a y. All right, so maybe there's some way that I can get y to be replaced with something else. Maybe there's something that I can do. Maybe this equation of the semicircle. Maybe that's gonna help us a little bit. Anybody remember the equation of a circle? No, I'm talking about like equation, how to graph a circle. Anybody remember that?
Very good.
X squared plus y squared equals r squared. No, we don't remember that. That's on your brain. Okay. That's the stuff.
Yeah.
It's not on there. It's not on there. Don't worry about it. So we've got x squared plus y squared is equal to r squared.
You should have said maybe so I'll take that off.
No, just I'll take this off the quiz. No, just I'll take that off.
LOL. Gotcha.
All right, so we subtract over the x squared minus x squared. And then we square root it. Now, I don't even need to worry about negative y value, right? Because when I take the square root, I've always got to write plus or minus. But does the negative y value in this instance exist? No, because I'm only looking at a semicircle. I'm only looking at the top half of the circle. So I know that y is equal to r squared minus x squared. So that means that I've got a is really equal to 2 times x times the square root of r squared minus x squared. Now, you may be thinking to yourself, whoa, we just replaced another variable with something else. Now, how can we differentiate? Now we've gotten 2 variables again. I've got to figure out some way to do r. But here's the difference about y and r, is that I could change how I drew this rectangle, right? And that would give me an x and a different x and a different y. But is r ever going to change? So r is just like a number. R is just like a constant in this case. The semicircle radius is not going to change. What's going to change is x and y. So when I differentiate this, I'm going to treat it like a constant. I'm going to treat it like a number because it's something that will not vary. It's something that will not change. I could just make this like 5 if I really wanted to, and it's not going to change the outcome. Okay? I could treat it like a constant and it will not change. All right, so let's differentiate. I'm going to rewrite it because it's going to be a little bit easier to differentiate. I'm going to say r squared minus x squared to the 1/2 power. Okay, because square root is 1/2 power. All right, so let's take a prime. So a prime is really going to be equal to, okay, we got a product rule. We got a product rule with a chain rule in it, right? We have a product rule with a chain rule within it. All right, so differentiate 2x, that's just 2, times r squared minus x squared to the 1/2 power. That's f prime g, plus g prime f. All right. Now, I would put the 2x here in front, and then I would bring the 1/2 out front and take r squared minus x squared. And then I differentiate the inside. However, what happens with r squared when I differentiate that? Does it become 2r? It goes away because it's a constant. It's just a number, remember? It's not a variable. It is just a number. What if this had been 5 squared? What would have happened with 25? It would have just gone away when I chose to differentiate it. So r squared is actually going to just go away when I do the derivative. So this is actually going to end up being just the derivative of this negative x squared, which is a negative 2x. That's times a negative 2x. That's not minus 2x. Because again, the radius is not going to vary. It's a constant, so we can treat it like a constant when we differentiate. Yeah?
Wouldn't r squared minus x squared be to the negative 1/2 now?
Oh, I'm sorry. Because I forgot to subtract 1, didn't I? Look at that. Nice catch.
Thank you.
That was freaking out here in a second. Okay. Yeah, again, did we catch that? What I did wrong there? I didn't subtract the 1. Okay, so now let's reduce it a little bit. So this is a prime is equal to, all right, we got 2 times the square root of r squared minus x squared. I'm going to put it back into the square root because it's a little easier to write like that. Now, this is going to go into the denominator, right? This to the negative 1/2 power. And look here, this 2 and this 1/2 is going to cancel out. So it's going to be r squared minus x squared in the denominator and the square root of that thing. And then in the numerator, negative 2x squared. Because I've got an x and a negative 2 still left over. So negative 2x squared. Now, just to simplify things, just to get it into one fraction, I'm going to do a common denominator here. Okay. So I am going to multiply the left term as, I'm going to do the square root of this denominator, r squared minus x squared. Right, just to get it as common denominators. All right, so what is that going to accomplish? That's going to take 2 times. Now, what happens when I multiply two things and they both have the square root on them? Square root goes away. So r squared minus x squared all over the square root of r squared minus x squared plus negative 2x squared over the square root of r squared minus x squared. Oh, sweet. Because look what's going to happen. When I distributed this in and then I add, look what's going to happen. I'm going to get 2r squared, right? I'm going to get 2r squared minus 2x. Oh, it's not going to cancel out. I thought it was going to cancel out. No, it's not going to cancel out. Oh, bummer. 2r squared minus 4x squared. It's just going to double. So I guess that's my derivative. Is that what I have on my paper yet? 2r squared minus 4x squared all over the square root of r squared minus x squared. Okay. So that's my derivative. I know that my minimum or maximum is going to come at where that equals 0. It's going to exist at where that equals 0. Well, where is this going to equal 0? Where the numerator equals 0, right? Okay. Well, 2r squared minus 4x squared equals 0. So that means that 2r squared is equal to 4x squared. So getting this in terms of x, I divide over, and then I square root. I'm going to get r squared over 2 is equal to x squared. And then I square root it. X is equal to the square root of r squared over 2. So that's really just r over the square root of 2. Now, yes, go ahead.
So when there's a number under the square root, if you're adding, subtracting to the limit of those squares, you can't like take it down to the original, only if there's one number under it. Like you could take down r squared to an r, because there's like r squared minus x squared. You couldn't do that.
Right, correct. Okay, so now, yeah, like that's why I can do that piece, because it's just a single variable. If it was a product, I could do that as well, but not a subtraction, not a difference to the sum.
You can do that when you're all flat.
Yeah, if this was like the square root of x squared, r squared, that would be just xr. Yeah, that works like that. Okay, now, I guess I should have considered where the denominator also equals 0, because remember that the critical points are not only where the function equals 0, but also where the function does not exist. But in this case, I would have said r squared minus x squared equals 0, right? Because I'm looking at the bottom here. I would say that this is true, but when I go to square 0, that goes away, right? I would square 0 over to the other side. So r squared is equal to x squared, so x is equal to r. But can that happen? Can x equal r? No, because then there would not be a rectangle, right? That would be it. There would be no rectangle. So this gets thrown out. That does not like exist within our scenario here. So the only other location is r over radical 2. So that's my x value. It says to find the area. Well, the area is what did we say? It was 2x square root of r squared minus x squared. And therefore, so R is equal to, oh, yeah, okay, sorry. Never mind. I couldn't read my handwriting for a second. So 2 times r over radical 2 times the square root of r squared minus x squared. Well, r squared minus, and then if I square this, that would be r squared over 2. Right? Get ourselves some common denominators in there. Actually, you know what? I don't even need common denominators. Those are like terms. 2 times r over radical 2 times, look, I've got 1r squared minus a half r squared. So it's 1 minus 1/2 is 1/2 r squared. I square root that, and look at what I've got. I've got r over radical 2. This is 1r squared minus, technically, a half r squared. So 1 minus 1/2 is 1/2. And then I square root that. Square root of 1/2 is like putting it over the radical 2. And I square root r squared, and I just get off.
Your arm was going
I know, I'm sorry. I'm sorry. I'm sorry. And so look at what happens at the bottom. Look at what happens at the bottom. These 2r square, the square root of 2's will just become a 2. So this is 2 times, here, let me make it a very curvy r. There we go. R over 2. R squared over 2. So that would just be r squared. So the area of this thing is actually just r squared. On the homework? I don't believe the whole graphing piece. How about this? Let's not take our quiz. We'll make tomorrow, the rest of today, a work day. Let's try to get our homework done tonight, and then I'll answer questions tomorrow.
Okay, I can't do the first.
Yeah, you want to explain the
I can't do the. Hold on, let me turn off the video real quick. I can't do number 1.
Actually,